One of the fun parts of ChatGPT, of coding with ChatGPT, is that it's non-deterministic, so you don't know what you're going to get. So I didn't practice this part I'm going to do now, but even if I did practice, it wouldn't really help because, well, I've practiced before for the previous streams, and for one of them, and it didn't really help me because when I did the live stream, it didn't generate the code the same way as during the practice. So it's a bit of a challenge. But I want to start by looking at a quick recap of what we did before because it was a few days ago, and you might not have watched the previous stream. And the streams are on various social networks. It's on LinkedIn. I've got it on YouTube, my YouTube channel, on Twitch, on Twitter, and I've got a private Facebook group for my students, my Java specialists, teachable students, which I stream there as well. So what I did before was we did a binary tree, a very simple binary tree, and we extracted an interface for that. So if you look at the binary tree, we just have add, contains, remove, size, and max depth. And the max depth is really a debugging function. It's there to test how deep the tree is. And the first tree we wrote, well, ChatGPT wrote, and I copied and pasted from ChatGPT basically into the code, is this simple tree, the simple unbalanced binary tree for elements which are comparable. And we've got nodes. The node over here is a private static class with left and right. It's comparable, and so you can set the values left and right, and you can easily insert and add and so on and remove elements from the tree by adjusting the nodes, left and right nodes. So the methods that we have here are add and add recursively add. So it's going to be calling add recursively until it finds the right place to add. Then we've got the next one we have is contains. Contains again does a recursive search down there. If it can't find it, it'll just return false. Then the max depth, the first version we had was recursive, and I asked ChatGPT to convert it to an iterative method because our tree became too deep, and this wouldn't actually work. It would give a Stack Overflow error. However, what I forgot is that the add would also is also recursive, so add and contains would also throw Stack Overflow errors once the stack gets too deep, or the tree gets too deep. And it's around about 100,000 or so you're going to get an exception. And of course you can make the stack bigger, but I didn't want to try that. I just wanted to I abandoned this and we did another type of tree. But we could convert each of the methods to an iterative method rather than a recursive method. You can always convert recursive to iterative, usually by having a stack. Like here we've got a deck, an array deck of what was before, and so we're no longer going to run out of stack space. At least, you might run out of memory, but nowadays we have a lot of memory, so that wouldn't really be a problem. So this was max depth again. This was generated by ChatGPT. The IntelliJ AI assistant did that for us. And then we had remove, which again was recursive. Size counted how many elements there are by iterating through. And if I remember correctly, there was another mechanism we used, but it wasn't as reliable, so we replaced it with this. And then the last one was the iterator, which we didn't completely implement. We didn't implement the remove, so what we did was we just have has next and next and remove throws an exception, and I'm happy with that. I don't really have to implement remove here because this is anyway a partial implementation. And the problem we had with a simple unbalanced tree is that if you insert elements in the correct order, in the sequence, in other words, you're going to have, for example, A, B, C, D, E. A will point to B on the right hand side, B will point to C on the right hand side, C to D on the right hand side, D to E and E to F always on the right. So what actually happens here is that your tree is going to be order n lookup. So if you want to add an element, it's going to take order n, look for an element, it's order n, and the linear cost is, of course, problematic for two reasons. The first reason is that our nice recursive methods throw out of Stack Overflow error, and the second problem is that it becomes very slow to add elements and to look for elements. And we did this in a test. So there's a test here that says binary tree test, and the binary tree test tests how long it takes to do a contain. So this over here is a time test, and if you run that time test, you'll see that the unbalanced one is quite slow. It was about 9 seconds, whereas the balanced one was much, much faster. All right, so then I wanted to do an AVL binary tree. Now the AVL binary tree is, AVL stands for some names, some Russian names, I believe, which I don't remember. Apologies to them. But I have written an AVL binary tree a very, very long time ago. It was either 1990 or 1991. I cannot remember it, but I do remember the basics, very basics. And the AVL tree is very well balanced, but it's a bit of effort and time to keep it balanced. So there's a cost for balancing it, maintaining it, which is bigger than other solutions. But with this, we have a really good performance. So you end up with, if you have, for example, 1,000 elements, you can say log 1,000 of 2, log 2,000, it will be only 10. So the maximum depth is 10. All right, so we've got tests for this, and I'm going to run the test again for the binary tree test. Let's call it the binary tree test over here. This runs both of them. I think it should run both. Yeah, so it's AVL tree. The unbalanced one is quite slow. You can see the max depth the unbalanced contains takes about 9 seconds, whereas the balanced one, the AVL tree, only takes 16 milliseconds. So that's quite nice. And of course, this is not proportionate because it's a different order. The unbalanced one is order n, and the balanced one is order log n. So as n increases, the difference is going to be really, really big, very large. All right, so what I wanted to do for this stream, and apologies if you've watched the previous ones and why is Heinz not getting onto the red-black tree? The red-black tree is actually used in several places in Java. So if you, for example, take a tree map, the tree map, or rather the tree set contains a tree map, which is a red-black tree. And the idea with the red-black tree is that we optimize efficiency in order to modify it quickly, but the worst case scenario is 2 times log n. That's as far as I know. And I've actually never written a red-black tree. I've looked at the code and I've read a little bit about them. Not that much, just enough to get into trouble and to know what problems to avoid. But that's what the red-black tree gives you. So it could be a little bit slower than AVL binary tree, but shouldn't be much worse. So how are we going to do this? Let's do the following. Let's copy this to red-black tree and call it that, red-black tree. And then we'll ask ChatGPT to convert it to red-black tree. And let's get rid of the comment because it's not going to be correct anymore. And also this as well. And I'm going to select all of this code over here. And I'm going to say AI actions down here. And I'm going to say, no, it didn't work. For some reason, I'm really unlucky with getting this AI to work. So we're going to say generate code. And I could say new chat using selection, but let me try generate code and see if that works. Convert this AVL tree to a red-black tree. Okay, and we'll see how well it does it. I'm going to assume it knows the theory behind it. If that doesn't work, and I don't know if that will work or not, as I said, this is not a very deterministic process. Sometimes it works, sometimes it doesn't work. But if it doesn't work, then I will take the normal tree, no code generator, because that didn't work too well. Let's try again. Maybe that'll work the second time around. If that doesn't work, then I'm going to take the unbalanced binary tree, and I'll try and convert that to red-black tree. Okay, it's doing something now. It's got a color over here, red and black, two different colors, both as Boolean. And it's interesting that they're choosing a Boolean for the color, not rather than, for example, an enum. I would have probably taken an enum for it, not a Boolean. This seems to me like what an inexperienced programmer would do as a premature optimization, right? So your key, your value, your left and right, those are each four pointers, which will be 4 bytes each. Int is another 4 bytes, so you're looking at 12 bytes, and then for 16, 20 bytes, and then another 1 byte for the color. And then we might as well have an enum, a pointer to an enum. It would take the same number of bytes, I think, as if we just have a Boolean. So it's like a premature optimization, but we'll leave it like it is. So this is what they do. They change the node. It's now got again, what they've done is they've put, interesting, they've made k comma v. Now that's interesting. I wonder why they've made it into k comma v, key comma value. I think what they've done is they've actually made a map out of it. I don't want a map. I want it to be the key should be the value as well. So make key be the same as value. We'll see if it does that, because this is like a map. It's like a tree map. What has that done now? So the key and the value is the same now. Again, what it's done is it's sort of borrowing the generic from the red-black tree class, which it did as well previously. And in other words, the private class node is not static. I prefer it to be static. So once it's finished, I'm going to ask it to make it static instead of me having to do it. And then we'll see whether it manages to do this or not. I've got no idea. It's interesting. What's interesting here is that they've got the n, the capital N being the number of nodes in the subtree. That's not what you do typically as a Java programmer. Normally, a field would be lowercase written, and I'd probably rename that to number of nodes in subtree, so that you don't need to have an explanation. If the variable has a good name, you don't need to explain what it means. It's already done. All right. So should I see if that works? Let's see if that works. Let's say accept all and see what is missing. So there's some things missing. It didn't red black tree should be cleared in the file name. What is it called? Okay, I'll just rename it to red black binary tree. Okay, I think that's the only mistake it's complaining about. As I said, I have read this before. I've read the red black tree implementation in TreeMap, but I don't remember how it works. I just remember sort of it's even added assertions. That's interesting. That's interesting, actually. It's almost like it's not quite sure that the code's correct, so it adds assertions in there. Very interesting. And I'm wondering if everything seems to be implemented. Right. So we also have to say implements binary tree. And I bet there are some methods which haven't been implemented yet. Yeah, let's do it this way. And we can leave out the definition over here. Right, get rid of that. Okay. Sorry, it must be T implements binary tree T. Okay, is that right? Do I need to have that? No, I do need the comparables here as well. Okay, let's put that back. Like so. but now I'm missing some methods which I expected. So there's actually quite a few methods in here which are not not there. So uh, so what do I do? What am I supposed to do now? So what I think I'll do is I'm going to take the normal tree, the unbalanced binary tree, and I'll try and convert that to the red-black tree, because it might be going from the AVL tree to the binary red-black binary tree wasn't the easiest way of doing it. Or I can try and add the methods, such as add and contains, but let me rather start again. So I'm going to delete that, and I'm going to take the simple unbalanced binary tree, which has no balancing at all, and copy that to the red-black binary tree, red-black binary tree. And now we'll start this whole thing again, and we'll see how well this works. So select all the code, and this time I'm going to be a bit more specific. I'm going to say generate code, convert to a red-black binary tree, implementing all the methods in the binary tree interface. All right, let's see if it does it properly now. I should have added some more, like, also make sure that the node class is static, but it's actually done it this time. This time it's made the node class static. Isn't that interesting? And this is what's interesting with this, is that it's each time you run it, you might have different results. So it's added a lot of additional jobs in the testing sphere. Yeah. All right, so let's see how this looks if it's implemented everything. Let's see, it's done the implement binary tree, so that's good. And it's got the add method. Let's try and accept all and see how that looks. So it's complaining about something. It's complaining about methods not being there. There are a bunch of methods not there, which it didn't add. So let's add them. The rest of the code remains the same. Are you serious? Okay, well, we'll copy the rest of the code over and see if it works. Okay. I guess we can try it. What's the harm in trying that? So the rest of the code would be what's missing is contains, remove, size, max, depth, and iterate, are those ones. So let's copy them over. So it's contains, let's start over here, contains, was remove also there? Okay, let's copy contains over first. Contains, copy. It's almost a shame to do it this way. We should actually have some of these methods being. Oh no, I didn't want to do that. Copy this without. So that's a little trick I used. Let me do that again just to show you. If I paste it, it says, "Hey, what about the node class?" And I just press escape to not import that. Then it uses the node class in here. Okay, so we want to have the remove can't possibly be the same. I don't believe that's correct. So I'm going to generate that. I don't believe it's going to be the same, because it's red-black tree. If you remove something, it should remain balanced. Let's see what it says over here. Okay. So yeah. So I don't believe that that's correct. So let's go and let's generate that. So we need to say generate code, add remove method. So let's see if we can do that. Remove of the value, and yeah, this looks more like it. That's more because it's going to have to do some rotating and some moving if it's going to remove an element to rebalance it. So that certainly is what I would expect. I wouldn't expect it to simply be, copy and paste it from the unbalanced binary tree. That doesn't make any sense. So let's accept all and see if that is correct. No, I think now it's put it, it's actually destroyed my class. So, all right, let's just, oh, it's actually copied that over my previous code. So let's implement the remove, and what we'll do is we'll say implement, and we'll see if we can manage that. Add actions, generate code, implement method, remove, and see if it does it. So I don't know if that's going to work. I'm still learning how to make these methods fit into the right place. It's all a little bit of mystery, but eventually we'll get the hang of this stuff. I think like this is one of those things that I think is worthwhile actually learning, because as we become good at it, we'll be able to. How do you get this? All of this selected. We'll be able to actually be quite efficient at this, at using this AI. I'm hoping at least. All right, so I've added the remove. There might be some duplicate code in there, but that seems to be what I need. Okay, I don't know if that's correct. We'll run the test in a moment and see what comes out. The other methods might be okay, like the size, for example. And the size we can actually move that up. So at the moment, the size in the AVL tree is this, and it's the same as we have in the unbalanced binary tree. So I'm going to go and refactor that. So how do you refactor? There's some shortcut, I can't remember. Move instant method. We're going to move this up. How do you move it? Move this up to superclass. So let's go to the interface, and we'll simply make that a default method here. So instead of public int, we'll say default int size, and that's going to use the iterator to count how many elements we've got. And so then I don't need that in here anymore. I also don't need it in the unbalanced binary tree. I don't need the size either. So let's go and search for the size. Delete that. It's the same. And I don't need it in the red-black tree because it's implemented already. The the max depth is going to look pretty much exactly the same, but it's a different node, right? The node class that we're using is a different type. So I'm going to have to copy and paste it again. That's actually the third instance of this. So really we should have something like this built into the tree. In fact, what we need is actually the visitor pattern. We need the visitor. So you can pass a visitor into the tree, and the visitor goes and visits all the different elements, also knowing where they are in the scheme of things. And then you could do this counting as a visitor. I'm not going to do that. Maybe I'll do that as another stream, actually. It might be quite a fun stream to do. But for now, I'm going to do another copy and paste. I don't like copy and paste, but what can you do? So we need to import the array deck, and I think that's all we'll need to do to make this one work. The last thing we need is an iterator, which I think will be similar to, I'm actually not sure, because I remember the AVL binary tree was a bit different on the iterator, and when I just copied and pasted it over, it didn't actually work, did it? It didn't work. So correct. So let me also generate the iterator. So we'll say again, AI actions. Oh, it's actually done something for me. Okay, implement that, and AI actions. New chat using new generate code. Create binary tree iterator for this class, and we'll see what it generates. Let's see if it's a proper binary tree iterator that we can use. Private class binary tree iterator. Again, it looks very similar to the one we had in the AVL tree, so it's probably pretty much the same. Let's copy and paste that over. And what I find interesting about this whole process is how much duplicate code we're getting. which is what we probably wanted to avoid. However, in the greater scheme of things, I believe this would be eliminated. You would actually have less duplicate code because, especially if you take something like Copilot, which can see all of your code, and in fact the whole of GitHub, everything in GitHub is there. So it could very well reduce the amount of duplicate code. All right, I'd footnote if this works or not, but I am willing to give it a try. So let's take our previous AVL binary tree test, and we're going to make this the red-black binary tree test. And it's going to, the only difference here, it's going to be a red-black binary tree. And this, before, the expected max depth was math.ceil of math log elements divided by math log 2. But now we actually expect it to be twice that. So this times 2 would be the expected max, but it could be less. It could be less than that. So it's not necessarily that it should be less than that. So I might have to change the way this code is checked. Instead of saying assert equals, I should say assert true that expected max depth of size. Let's do the following. Let's put this. Let's print this out. So we're going to put this into local variable max depth, and we're going to just print out the value of max depth so we can see it. See what we get there for the max depth. But then what we'll do is that we will say expected true that the max depth is bigger or equal to the max depth, right? The expected max depth is bigger or equal to max depth, all right? All right. So let's run the test and see what passes and what doesn't pass. This is like walking at a tightrope without... Oh, interesting. The max depth is actually, what is it, 14, right? That should have been... I think 14 is actually a pretty good max depth. Interesting, very interesting. So maybe it actually balanced it better than it really needed to. And I want to try with more elements, because I want to check that it actually is a red-black tree and not just an AVL tree with the name red-black penciled on. I think it is, but I want to check that. The other part is that we haven't got concurrent modification exception built in properly. We had the same problem before where we needed to retrofit that. Do we have mod count in here? Yeah, we have mod count. Add increases it. Don't know if you heard that cough or not. I tried to mute myself. We'll see if it works or not. So add increases mod count. Remove doesn't. Okay, so remove should increase the mod count. So we need to change it, remove to also change the mod count. Mod count plus plus. Actually, this is not completely correct because it only should change it if it has actually changed it. Whereas if you try to remove something which isn't there, then it wouldn't necessarily work. Now it still doesn't work. The other thing we need to look at is whether or not we look at that with the iterator. Probably don't. And you see this doesn't actually look at the mod count. So what I'm going to try, I don't know if this is going to work. I'm going to copy it over from here. Just copy this iterator over to the red-black binary tree. Copy and paste it. Not import any of that. Oh, the other thing is there's a bunch of different things here. Okay, let's import this first of all. Okay. Oh, that's wrong. Import that. All right. And then the other part is we need to import the no such element exception, which we didn't do before. And this one we need to import as well. All right. So I've done a bunch of additional code, and then I need to just rename this to the binary tree iterator, and then we should be good to go. So let's run the test again and see whether that works. I do think we needed that. I do think that we needed the what do I say? I think we needed to have in there the what am I thinking now? My mind's gone blank. I've forgotten something. Needed something there. Anyway, okay. So let's go back to the binary tree test. This over here is the test depth. The expected max depth uses that, and the expected max depth. Let me run both of these. So we're going to run both the tests, all three tests. Just run them all three, and the simple tree max depth. Oh, I see that we've already printed that out. So the simple tree max depth, we printed out somewhere else. All right. So the max depth is 14 for the AVL tree, and it's also 14 for the red black tree. All right. Good. So let's do the following. Let's instead of having 10,000, let's add for this test the test depth. This is one that we ran. Okay. So I'm going to do this a bit differently. I'm going to copy and paste this test. And I'll just put this into the red black tree test because I want to just do a quick check of something. So we're going to, oh no, let's do a test public void test bananas. I'm going to delete that now in a moment. So just test bananas. Just going to do some banana testing. And what I'm going to do is I'm going to make it much bigger. So I'm going to make it 1 million. 1 million. Like that, 1 million. One moment. All right, so 1 million. Like that. And we're going to put them in and add them all in there and then print out the max depth without doing any assertions. So I want to run that and see, and I want to see if it's 20. I see it's 20. So this is probably not actually a red black tree. It's probably the AVL tree. or maybe there's some other reason why it's exactly like the most optimal. If I did this with a tree map, it wouldn't be exactly log to n. So quite possibly, it's actually not done a red black tree. Quite possibly, it's too well balanced, right, to actually count for that. So yeah. So if you're like really worried about this taking away your job, I don't think you need to worry too much. I mean, it will eventually, but not this year, or at least not this month, or at least not this version this month. All right. So let me try something else and see whether this does a better job. So I'm going to take this code, and we're actually going to copy and paste it directly into ChatGPT 4 and say, hey, do you know how to convert this to a red black tree and see if it does a better job. So I've got a ChatGPT 4 subscription, which I think might be quite handy. So let's make a new chat here, ChatGPT 4, and I'll say convert this simple binary tree to a red black tree in Java, implementing all the public methods. Okay, so we'll see whether it does a better job now. So let's see, chuck. And one of the challenges with this is always the size of the what do you call it? Of the query that you send and the query that comes back. And if it's too big, then it won't do the job properly. So I'm actually complaining here that it's too good. The implementation's too good because it doesn't match my experience with the TreeMap and the HashMap in Java. And of course, they might be more optimized in other directions. So it might well be that it ends up doing exactly the same. So complete. So it again didn't finish it. I don't know why it doesn't do it. Please add all the methods. Well, maybe it does that so that students can't cheat so easily as possible. Because why don't you do the whole thing? I don't get it. I don't understand why it doesn't just do the whole tree. I mean, it knows how to do it. Why doesn't it just do it? It's really weird. It almost seems, I mean, at the end of the day, we're going to use the tree map, right? We're going to use that. Maybe I should say please, and I should say I promise I'm not using this as a student assignment, and I promise I'm not doing a job interview. Just implement this stuff. But maybe it's I don't know. It's strange. So it's carrying on and on, but not actually doing the work. Maybe it's just too big, because the end result will be too big. But this code looks very similar to what's generated by IntelliJ. Red, black, true, false, and then you've got one thing which was different. The one version we saw also had the depth as well in part of the node. I don't know if it was in the latest version. So this one here looks the same. So it's got red, black, tree. That all looks the same with the value left, right, color. That's all the same. Interesting. So I don't know what to do, because the result isn't exactly what I expected, but I don't know whether my expectations are wrong. Maybe my expectations are simply wrong. Maybe this particular or that particular data set happens to give you the most optimal version. So let me try one more thing, and that is to change the order of this. So can you say reverse? I can't say reverse, can you? I can say dot to list. No, I can say, yeah, let's do this way. So I'm going to say dot to list dot reverse. This is the Java 21 method, and then dot. I want to make a. Actually, that's all I can do. Dot, yeah, just like that. So this gives me back a reversed view on the list. And I want to see if that's also 20. It probably is. But, oh no, that's not. Okay. So that's not 26. Now, if I run this code with the AVL tree, I think it would still be 20. I think it would. But I wouldn't bet money on it. And, if I'm not willing to bet money, it's probably probably not true. I'm very careful with betting money. All right, so this one's 20, right? This one's 20 is what I expected, and the other one is 26. So maybe it is correct. Maybe the data that I'm sending it simply is such that it happens to work out this way. All right. The other thing I wanted to try. Something else I want to try, which is this now is at the moment it's a simple tree of strings, right? If I have a tree of integers, it might actually be a bit different. So let's just try this, not with the AVL binary tree, but with the red-black tree. Let's try over here. After we've run the test bananas, we're going to say, and what I'll do is I'm going to copy this code over to the other code, to the binary tree test. I'm going to change it to be reversed. Right, so that's going to be reversed, and the depth on the reversed one for the unbalanced one will still be 10,000. For the AVL tree, it'll still be 14, and for the other one, it's be a bit different, I think, a bit more. All right, so red-black tree, if you look at that, what I wanted to try, just to see whether it works, is to say var tree equals new red-black binary tree of integer. So it's now an integer tree. And instead of making it do that, I'm going to say dot for boxed. No, I'll do it in the right order. Dot for each tree : add. So it's going to add them in the right order from 0 to 9999. And then we're going to work out the max depth on the red-black tree. And I want to see whether that will actually be the max depth is 0. It didn't, for some reason that didn't work. Oh, yeah, we need to do the tree over here, not the. There we go. That's it. Using the wrong tree. That's again 20. Interesting. So, so it had nothing to do with the fact that it was a string rather than integer. I was just wondering whether that had some bearing on it, but it obviously didn't. So let's get rid of this test bananas. And we now have a test that tests a bit better. It's a bit more rigorous. And it's going to test the maximum depth of these three trees. First of all, the unbalanced binary tree, which is going to be order n for this data set. The simple tree max depth is 10,000. And the AVL binary tree is 14. That's the most optimal version. And then the max depth here is 18. Max depth 14. And here the max depth is 18. Okay. The simple tree max depth, that's a different test. For that test, we are again going in the sequence, so from 0 up to the size. So I'll leave that one as it is. It doesn't matter so much. But this one, max depth over here, this one was interesting. And so it seems to be working. But as I said, I'd have to walk over to my cupboard and pull out the Art of Computer Programming to have a look at how it works again. I've never implemented that, never needed to. I always just use the TreeMap. Now, I do want to go into HashMap at some point, and the HashMap is quite an interesting feature in Java. But the standard HashMap actually uses a red-black tree if you have a lot of clashes. So to resolve the clashes, we use a red-black tree. But this is all fun. I might actually change direction on this, on these streams. At the moment, they're just looking at data structures because data structures have been around for forever. For millions of programming years. If you measure the way that programming changes over the time, it seems like forever. But they've been around for a long time, but and so they should be very well understood. The same with design patterns and algorithms. So it's fairly easy to test that, to test how well it does it. But I don't know if that's a really good test overall because we haven't really seen it do such a good job. I mean, we've managed to get it working without having to understand how red-black tree works. However, there are some interesting limitations. What we saw is as the code became more complex, the prompts or the results had too many tokens. I think that's the problem. Too many tokens appearing, and then it just says, okay, well, just do the code yourself. I'll give you an example of how to do it, but I'm not going to do it for you, which is kind of unfair, right? I mean, maybe it says, well, if it's a red-black tree, obviously a student, and you're trying to do a homework assignment, I'm not going to do that for you, which I guess might be a valid thing to say, because no one in their right mind would. I mean, I don't want to say it like that, but you wouldn't really want to implement a red-black tree in Java. You just use a tree set or TreeMap, unless you are one of the developers of the Java util packages. Then maybe you want to use red-black tree, but otherwise you're not going to write one. You'll just use what's available. Same thing, you're never going to write a bubble sort. I bet if I say, hey, write a bubble sort, it'll and you'll have a bubble sort done. But I mean, no one's going to write bubble sort. You're probably not going to write a quick sort either. You're going to just use list.sort in Java. So these exercises here are, I think, quite fun. I think it's quite fun playing with ChatGPT. and seeing what it can do, kicking the tires. And it's a bit like, 2000 2007, I think it was, beginning of 2008, beginning of 2008. So I bought myself this little Suzuki Jimny in 2007. I live on the island of Crete, and a friend came to visit me, and we went driving all over Crete. And so it's a brand new car. It had, I don't know, 1,000 kilometers on it or something. It was very, very new. And it's a little dinky little 4x4. It's quite capable actually. And I was with my friend. He'd come to visit me from South Africa, and we went to the south of the island, and I parked above a beach. It was a beach of like loose stones, small loose stones, like not very small, like about this size, small, and I said to him, Andrew, do you think I can drive on that with this Jeep? And he said to me, I wouldn't try that, my friend. And I went down and I drove. And as I was driving, I was sinking deeper and deeper into these loose stones. I knew I'm in trouble. And I also knew if I stop, I'm in bigger trouble, because I didn't have a shovel or anything to get us out. And I didn't really want to get stuck on this beach and now have to go and look for a tractor to pull me out and be like really embarrassed, So I just kept on going, and I like all cool, did a U-turn somewhere over the beach, and then went out again, and I thought to myself, oh my goodness, I had like bad dreams about that for a while, getting stuck there. Luckily I didn't get stuck, but and the beach where I go running every morning, it's a very deceptive beach, because on the one side there's the sand is fairly hard. That's where I go running, and the other side it's you just sink in, And I've several times seen 4x4s stuck there where it's soft. They do the same thing. Oh, let's go drive on the beach. It's of course illegal in Greece now, but they do it anyway. And so they drive down, they drive around the tree, they drive to the other end where it's soft. They don't know it's soft, and then boom, they're down. It won't move anymore. They're stuck forever. That's how I feel working with ChatGPT on a live stream. I feel like I'm in my Jeep, in my Suzuki. It's not a Jeep, it's a 4x4, and I'm looking at this beach and going to myself, I wonder if I can drive on this. And my friend's saying, no, don't do that. It's not going to work. And I do it anyway. And I just managed to get out. I don't know how, but I just managed to get out. That's what it's like coding with ChatGPT at the moment. But it is making amazing progress. And there's this one, I don't know if you've seen that. I saw this one thing where they've got like the whole thing automated, the whole development software engineering process automated, and you say, hey, I'm looking for an ERP system that does invoicing in a rotational basis, and invoicing and stock control, and it goes like chicka 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 chicka, and then all of a sudden you've got this, with pull requests and Git repositories and check-in and everything done. It's like done. Of course, it's not at all what the customer wants, but it never is anyway. So I can imagine that being quite fun for doing, prototypes. But yeah, I don't remember what that was called, Devon or something like that. I think Devon was the name of that virtual software engineer. It's a funny idea. It's a really funny idea. And the other thing with prompts is, if you write a prompt, a ChatGPT prompt, first of all, the end result can't be too big. So you can't say like, just write this whole program for me. It's just not going to work. You can do piece by piece and have a conversation. And the mistake a lot of people is that they think that they want to get the perfect prompt to get the perfect answer. But most of the time, it's going to be a bit of backwards and forwards until we get the right answer. All right, this went longer than I thought, but it was a lot of fun. Too much fun was had. If you like these streams, please comment. Please just say, Hans, continue doing this. I'm enjoying them, and as long as I enjoy them, I'm going to continue doing them. If I don't enjoy them anymore, I'll probably stop. But let me know, please, and hope you enjoyed this. All right, until the next time. Bye.